Hi, I'm David.
Hi, I'm Nick.
We are the 2D liquid metal actuation team. This semester was supervised by Saige. So over the past year, the 2D liquid metal actuation team has made advancements in actuating liquid metal in 2D planes. At the top right, this was one of our first designs, which used nickel electrodes, a PDMS well, and gallon stand submerged in NaOH. With these designs, we developed a working graphical user interface that allowed us to move the liquid metal with the simple push of a button. And through numerous tests, we found that we could also use stainless steel electrodes in our designs. And with our new electrodes, we started looking into how different voltages affect the velocity of the liquid metal. But before we look into the results, we need to understand how it works.
So this is how it works. Our liquid metal gallon stand at room temperature is in a liquid state, and sodium hydroxide solution is poured into our container of about half a centimeter in height. Our liquid metal is then inserted carefully into our container of a diameter of about half a centimeter as well. In order for our experiment to work, we have to make sure our liquid metal is fully submerged in our solution. Otherwise, an oxide layer will form and thus preventing our liquid metal from moving. This means the more contact it has with the air outside, it creates more net forces preventing the liquid metal movement. We use nickel as well as stainless steel strips as electrodes placed along the walls of our container to actuate our liquid metal. Continuous electrowetting is used to move the liquid metal towards our electrodes. This is our setup for our project. First, we have a computer with the Arduino program connected to the Arduino itself. The Arduino sends signals through the H bridges to turn on different electrodes along the container. These H bridges are powered by an external power supply in order to apply stronger or weaker voltages. Our project consists of a 3x3 cutout of PDMS. 3 nickel strips are placed on each side of the container, giving us a total of 12. Half a centimeter of sodium hydroxide solution is filled and half a centimeter diameter of liquid metal is inserted. One problem we ran into with this is that the liquid metal started sticking to the electrodes. So like our nickel design, we replaced our nickel strips with stainless steel strips instead. Although nickel is more conductive, we found that liquid metal does not stick to stainless steel as much. Stainless steel also works well with our other projects.
In terms of creating our software, we use two main programs. The first is Tinkercad, which we use to simulate our designs using LEDs to represent our electrodes. Through the use of Tinkercad, we gained insight on the basic principle of how our design works and how to set up code with an Arduino. From there, we were able to design our graphical user interface. So to do this, we use Qt Creator, which is a community-based open source, and this program allows us to create clean and organized user interfaces. This is one of the graphical user interfaces we made during the semester. And as you can see in the video, this graphical user interface uses LEDs, which represent electrodes turning on and off. With the help of Tracker video analysis software shown on the right, we were able to take data on the liquid metal's position. By focusing each frame on the liquid metal location, we could simply calculate the velocity by dividing the change in distance over the change in time. We tested a range of voltages ranging from 8 volts to 16 volts and found a maximum velocity of 10.5 centimeters per second with applied voltage of 15 volts. One thing to note is that the stainless steel causes the liquid metal to slow down the closer it gets to our stainless steel strips and eventually repel itself. In the graph, through simply turning on and off left and right electrodes at a designated clock period, we expect to see a graph resembling a square wave. As the liquid metal moves towards our electrodes and bounces off, we notice that in our graphs, it creates these spikes at the beginning of every clock cycle. So through our fabrications, we have found new designs that we can use to prevent the liquid metal from cohering to the electrodes by using stainless steel electrodes. We were also able to implement a graphical user interface using Qt Creator, and we started data analysis for the velocities of the liquid metal. Eventually in the future, we plan on transitioning to 3D actuation of liquid metal.